A quick note before I begin. As you watch this video, you will notice that there is a great deal less writing than appears on the screen and a great deal more talking. Some of you are used to writing down only what appears on the screen, but that will not be enough. Be sure to take notes on important definitions and ideas that I talk about, even if they don't appear on the screen for you to see. Also, while I have not written out each step in solving the problems that appear throughout the video, you should do this in your notes so that you can be sure you know how to do each problem. Jot down any questions along the way so that you can ask them in class. Hopefully, you remember a little bit about solutions from when we discussed them briefly in the fall term when we talked about matter. You may remember that a solution is a homogeneous mixture, which is made up of two or more pure substances. We discussed the idea that a solution is the same throughout, so that if you stuck a straw into the top of the substance and had a sip, it would taste the same as sticking a straw into the bottom of the substance and having a sip. A solution is made up of two components, a solute and a solvent. The solute is the thing being dissolved, while the solvent is the thing that does the dissolving. In the example shown in the picture on the right, the solute is the salt and the solvent is the water. As you may remember from earlier discussions, when the solute is an electrolyte, or an ionic compound, it will be broken up into ions when it dissolves, as you can see in the diagrams on the screen. When the solute is a non-electrolyte, or a covalent compound, it will not be broken up into ions when it dissolves. When making a solution, like dissolves like. This means that a polar solute will dissolve in a polar solvent, and a nonpolar solute will dissolve in a nonpolar solvent. A polar solute will not dissolve in a nonpolar solvent, and a nonpolar solute will not dissolve in a polar solvent. We can describe solutions in many different ways based on the amount of solute they contain. A solution is said to be saturated when it contains the maximum amount of solute that it can hold at a given temperature. Alternatively, it is described as unsaturated if it has less than the maximum amount it can hold. It is possible to make a supersaturated solution by heating the solution to dissolve more solute, then cooling it down so that the cooler solution actually contains a greater amount of solute than it should be able to at that temperature. A concentrated solution is one that contains a lot of solute, while a dilute solution does not. Do you think it's possible for a solution to be saturated but not concentrated? Is it possible for a solution to be concentrated but not saturated? Now that we have discussed different ways to describe solutions, we need to know how to measure their concentrations. We will talk about two different methods of determining solution concentration. The first way to describe the concentration of a solution is by the molarity of the solution, abbreviated with an uppercase M. The molarity is equal to the moles of solute divided by the total liters of solution. What is the molarity of a solution made by dissolving 45 grams of sodium chloride in water to make 55 milliliters of a solution? The first step in solving this problem is to think back to the formula for molarity, which is moles of solute divided by liters of solution. We need to figure out how many moles of sodium chloride we have. Doing the normal grams to moles conversion using the molar mass on the periodic table, we can determine that 45 grams of sodium chloride is equal to 0.77 moles. The next step is to figure out the total liters of solution. 55 milliliters is equal to 0.055 liters. Now all we need to do is divide the moles of solute by the liters of solution to get the molarity. Molarity equals 0.77 moles divided by 0.055 liters. This equals 14 molar. The second way to describe solution concentration is by molality, abbreviated with an italic lowercase m. Molality is similar to molarity, but differs slightly. Molality equals the moles of solute divided by the kilograms of solvent. What is the molality of a solution made by dissolving 15 grams of magnesium oxide in 95 milliliters of water? Similarly to the molarity problem we solved a minute ago, we need to figure out the moles of solute. 15 grams of magnesium oxide is 0.37 moles. The next step is to figure out the kilograms of solvent, which in this case is water. Because we know the density of water is 1 gram per milliliter, 95 milliliters of water is equal to 95 grams, which is equal to 0.095 kilograms. Dividing the moles of solute by kilograms of solvent, we find the molarity to be 3.9 molal. Let's assume that you have a bottle of Gatorade that you think is too sweet. What could you do to make it less sweet? If the Gatorade is already made, there is no way to take any of the sugar out of it. The only thing you could do is to dilute it with water so that the same amount of sugar would spread out in a larger volume. You may fill up a cup halfway with Gatorade and fill the other half with water to have a full cup that is less sweet. That scenario is something like what is pictured on the screen here. Assume that these beakers are 1 liter beakers. Let's figure out the concentration of solution 1 on the left. There are 6 particles in half a liter of solution, so the concentration is 12 particles per liter. Solution 2 on the right has a different concentration than solution 1. Notice that there are still 6 particles in solution 2, but the volume has been doubled from half a liter to 1 liter. Therefore, the concentration is 6 particles per liter. Solution 2 is only half as concentrated as solution 1. It is important to note the thing that is the same about solutions 1 and 2. The number of solute particles is equal in both beakers. What is it that is different in the beakers? Solution 2 has twice as much solvent as solution 1. In order to make solution 2 from solution 1, twice as much solvent was added to dilute solution 1. Keep in mind that the molarity of a solution times the volume of the solution gives you the number of moles in the solution. The number of moles of solute in solution 1 is equal to the number of moles of solute in solution 2. Therefore, the molarity of solution 1 times the volume of solution 1 is equal to the molarity of solution 2 times the volume of solution 2, or M1V1 equals M2V2. Let's look at what a sample dilution problem might look like. Pause the video while you read the problem to yourself. When you're finished, unpause the video and I will walk you through the answer to the problem. Before we even start to solve the problem, let's think, very basically, about what will need to happen. We will need to take some volume of the very concentrated stock solution and add water to it to make the solution we're looking for. First, let's pick out the given pieces of information. Keep in mind that similarly to the gas law problems we just finished studying, it doesn't matter which is 1 and which is 2, as long as the 2 parts of 1 are paired correctly together. The molarity of solution 1 is 0.150 molar, and the volume of solution 1 is 5.00 liters. The molarity of solution 2 is 18.0 molar, and our job is to figure out how much of solution 2 we need. Once we figure out the amount of solution 2 that is needed, we'll also need to figure out how much water to combine it with. In order to figure out the volume of solution 2 necessary, we will use the equation M1V1 equals M2V2. Plugging in the appropriate values for M1, V1, and M2, we can solve for V2. We see that V2 equals 0.0417 liters, or 41.7 milliliters. Therefore, we need that amount of the stock solution combined with water to make a solution with a concentration of 0.150 molar. In order to figure out the amount of water that is needed, we have to think about the total volume of the diluted solution. We want 5.00 liters total, and we know that 41.7 milliliters must be the concentrated stock solution. That means that the remainder, 4.96 liters, is made of water. Think back to the wintertime when it is really cold out. Oftentimes, salt is put down on the roads or sidewalks to help melt the ice that forms on these surfaces. What happens to the freezing point of water when salt is added to it? The freezing point decreases, which is known as freezing point depression, or the lowering of the freezing point. So water with salt freezes at a temperature below 0 degrees Celsius. Imagine what happens at the other extreme, to the boiling point. The boiling point increases, which is known as boiling point elevation. Water with salt boils at a temperature above 100 degrees Celsius. Things such as freezing point depression and boiling point elevation are called colligative properties, which are properties that depend on the concentration of solute particles, but not the specific identity of the solute. We can use two different equations to look at the effect that the addition of a solute to a solvent has on the boiling point and the freezing point. These equations are shown here. Delta TB, or delta TF, refer to the change in boiling point or the change in freezing point. They are calculated as any change is calculated, the new freezing point minus the initial or old freezing point. Let's say that we add salt to a solution so that the new boiling point is 105 degrees Celsius instead of 100 degrees Celsius. The change in boiling point, or delta TB, is 5 degrees Celsius. Kb or Kf refer to the boiling point constant or the freezing point constant. Kb and Kf are values that you can find in a chart that will be given to you in class. They are specific to each individual solvent, in the same way that specific heat is different for each different substance. M stands for the molality of the solution, and I stands for the Van Hoff factor, which we'll discuss further in a minute. Let's take a look at a colligative properties problem. First, we need a further discussion of the Van Hoff factor, which gives us the I value to plug into the equation. The Van Hoff factor is the number of moles a substance splits into when it dissolves. For example, when sodium chloride dissolves, it splits into Na plus and Cl minus, so the Van Hoff factor is 2. When aluminum chloride dissolves, it splits into Al3 plus and 3 Cl minuses, so the Van Hoff factor is 4. When magnesium nitrate dissolves, it splits into Mg2 plus and 2 NO3 minuses, so the Van Hoff factor is 3. Remember that polyatomic ions don't split up. Imagine that I added 50 grams of sodium chloride, or table salt, to a pot that contained 2 liters of water. What will this do to the boiling point? Before even plugging any numbers into any equations, let's think about it. It will raise the boiling point, as we know that adding a solute to a solvent elevates the boiling point. The equation of interest is delta TB equals Kb times molality times the Van Hoff factor. The constant Kb is equal to 0.52 degrees Celsius per molal, which was found in the table given out in class. This means that the boiling point increases 0.52 degrees Celsius when the molality of the solution increases by 1. We can calculate the molality of the solution by dividing the number of moles of the solute, NaCl, by the kilograms of the solvent. Remembering that 1 milliliter of water has a mass of 1 gram, 1,000 milliliters, which is equal to a liter, must have a mass of 1,000 grams, or 1 kilogram. Therefore, 2 liters of water has a mass of 2 kilograms. The molality of the solution is 0.43 molal. Because NaCl splits into 2 ions when dissolved in water, the I value is 2. Plugging these values into the equation, we get delta TB equals 0.45 degrees Celsius. This means that the change in the boiling point is 0.45 degrees, meaning that when you add 50 grams of salt to 2 liters of water, the boiling point increases by 0.45 degrees. Since the boiling point of water alone is 100 degrees Celsius, the new boiling point of the new solution is 100.45 degrees Celsius.